Hey everybody. The last section in chapter 8 deals with power. Power is the rate at which work is being done or the rate at which energy is being transferred. Rate is the key word with power. It's a per time quantity. Right? And like most of our significant quantities, there's an average and then there's an instantaneous version. Right? So average power we're going to symbolize by P with a line over it. It's not a vector. That's the average symbol. Is the work done divided by the amount of time it took to do that work. Okay, so this is amount of work done divided by time. Instantaneous power, as you might guess, is the differential version of that, dW dt. Power has units of, well, it's got a lot of units, but the ones we're going to primarily deal with in the SI system is the watt. So 1 watt, following the definition of power, and that's a big W for watt, named after James Watt of steam engine fame. 1 joule per second. The customary unit is the horsepower. Abbreviated HP, or symbolized by HP, and that's 746 watts. A little shy of a kilowatt. Okay, so just a little note. Power multiplied by time gives energy or work. All right. So, for example, if 1 kilowatt of power is consumed for 1 hour, the transfer of energy is going to be W, power times time. So 1 kilowatt at 1 hour is the kilowatt hour. All right, typical measure of electric power consumption, as we mentioned a couple of videos ago. All right, so for situations with constant or average power delivered to an object during a time interval, that's your expression. Okay, so W equals, I should use the capital W. W equals P delta T is used for average power delivered to an object in time delta T. Now, What if P is not constant? What if P varies with time? So if the power varies with time, use differential form and integrate. And integrate. All right, so that's the form that we showed in the beginning of this video. dW dt. Just rearrange because we're looking for energy delivered or work done. So you rearrange this and you get dW equals P dt. If you integrate these two, integral of dW equals integral of P dt. Can't take P outside the integral because we're assuming it's a function of time. Okay, T1, T2. This is for when P varies with time. Okay, so, well, the left integral is easy. That's just W. So the work done or energy delivered is T1 to T2 P dt. Now, if the power is delivered by a force, so remember from section 7.2 from last chapter, all right, we had this for work. Work was the dot product of force and displacement, or dW was F dot ds. Now, we can find the power that's delivered by a force by substituting this in our power equation, our power definition. dW dt. It's the same dW, it's work. So this is going to go in here. So our power is going to equal F dot ds over dt. Now we can separate that out into the force vector over ds times ds over dt. Now, ds dt is velocity, change in distance with time. So power is just force dotted with velocity, or the scalar form, force, velocity, cosine theta. Okay, so that's the expression for power delivered by a force. All right, so a couple examples to mess with this. So page 256, number 76. We have a car engine with efficiency of 25%. Okay, it basically means that car converts 25% of the fuel into usable work, into mechanical energy. The rest is waste, and that's a pretty typical number for cars. So the mechanical output equals 110 horsepower. Okay, so that's what's actually hitting the road. That's what's actually it generates to actually move the car. What we're asked to find is at what rate will this engine consume gas in gallons per hour. Okay, there are a few ways to approach this this problem. So, the first thing is to recognize that you have to look something up, right? You have to look up how much energy is available in gas. So, the energy available in 1 gallon of gasoline is 1.3 times 10 to the 8th joules. Okay, so 25% efficiency means to produce at 110 horsepower, the car has to use 4 times 110, or 440 horsepower. All right, so we got to get these guys talking to each other in units. So we're going to change the 440 horsepower into joules per second. So 440 horsepower, we can convert that into watts. That's 746 watts per horsepower. And that's 3.28 times 10 to the 5th watts. But the definition of a watt is a joule per second. So that just comes out to 3.28 times 10 to the 5th joules per second. Okay, so now we're talking the same units. So the fuel consumed per hour is 3.28 times 10 to the 5th joules per second. All right, that's what the engine consumes in terms of gas. That's 1 gallon of gas gives 1.3 times 10 to the 8th joules. Okay, but this is per second here, and we're asked for it in hours. So we have to do 3,600 seconds per hour. So fuel consumed per hour equals, so joules, seconds, so we get gallons per hour. We're good. 9.1 gallons per hour. All right. One more. Page 256. No, 265. Number 88. All right. So, to overcome air friction and mechanical friction, an automobile of mass equals 1,500 kilograms. I'm not going to rewrite the whole problem here. That's where it is. I'm just going to write the key parts. Of 1,500 kilograms requires a power of 20 horsepower from its engine to travel at 64 kilometers per hour on a level road. Assuming the friction remains the same, what power does the same car require to travel uphill at a slope of 1 to 10 at the same speed? Right? So this situation right here is required to overcome friction. No acceleration here, just overcoming friction on a level road. Okay, so find the power required to travel uphill at the same speed, 1 to 10 grade for the hill. Okay, so so here's our little hill. I'm going to put ground, I'm going to put my vertical and my slope. This is my rise and my run, 1 to 10. So my little car is going up this time. Okay, now, assuming the friction, air friction, ground friction, all that friction in the mechanics of the car and all that's the same. The only difference here is the car is now gaining potential energy because it's going higher. Right, so let's establish a rate of increase of potential energy. All right, so instead of just mgh, that's going to be mg delta h delta t. Because m and g are going to be constant. The mass and gravity are going to be constant. What's changing is its height, and that's what's changing the potential energy. Right? So that quantity is the speed, 64 kilometers per hour. Okay, this is the total speed, but it's on a slant, all right? It's on an incline, so I'm going to multiply that by 1/10 because this is the vertical component. Of the speed. All right, so this is 64. All right, this is the vertical component of that. That's what we're interested in, because that's going to be the only difference. All right, so now we got to change some units here to get things into our basic, our SI units. We got to change those kilometers to meters, 1,000 meters in a kilometer. Get rid of the kilometers. We're going to go from hours to seconds. 1 hour, 3,600 seconds. Hours are gone. Multiply that through and you get about 1.78 meters per second. Okay, so that's this quantity right here. So now the rate of potential energy increase is pretty easy because m and g are constant. So rate of potential energy increase is mg delta h over delta t, which equals 1,500 kilograms. I'm putting my units in just to make sure everything's okay. I think 1 meters per second squared. and then times 1.78 meters per second. Yes, all the units agree. Okay. Multiply this out and I get 2.1613 times 10. No. Nope, got an extra number in there. 2.613 times 10 to the fourth watts. Right. But since I'm given the initial power in watts, or in horsepower, I should convert this to horsepower so I can compare. So 2.613 times 10 to the fourth watts. 1 horsepower is 746 watts. So that's 35 horsepower. This is the additional power required to go uphill. So the total power required equals the 20 from the level ground plus the 35 equals 55 horsepower. The question also asks about traveling downhill. Traveling downhill? That's just the opposite. Total power required is 20 minus 15. Or minus, not 15, 35. 20 minus 35 equals 15. Negative 15 horsepower. So you're actually gaining more energy from going downhill, as you would expect. All right, so that's it for chapter 8, and we'll see you in class this week. Bye-bye.